All right, let's go ahead and get started. So I posted this on Canvas, but I'll go ahead and repeat it here. Test grades are in Canvas. I need to wait for 2 more people to take it, so I can't give those back to you just yet. But if you want to come to office hours today, I can show it to you. I just can't let you take it with you yet. But if you have questions about the test itself, please come to me. If you have questions or concerns about where you stand now that the first test is in the books, please talk to me. But yeah, we can go over specifics whenever. Just reach out and we'll set something up. Any questions before we get back into new stuff? Okay, so we talked about improper integration. I think last Friday was the last time we talked about it because we didn't focus on the test since then. But one thing we talked about was this idea, if you have an integral from some constant to infinity of this here, 1 over x to the p. I think we talked about a condition for what values of p does that integral converge. So maybe we should back up a little more. What does it mean for an integral to diverge or for an integral to converge? Right. So basically, if it diverges, the integral diverges if I don't get a real number from it. And it converges the exact opposite. If your integral converges, that means that over some interval, that definite integral yielded a real number of a finite real number value. So before we got into this section, every single integral we've talked about has been a convergent one because they've all yielded numbers. But now we're dealing with intervals that they're not closed, so they're not from this number to this number. Now these intervals are unbounded. So going from 1 to infinity. So now that we've kind of reset what those meanings are for a converge and diverge, under what conditions does this thing converge? So basically, what values of p make this thing converge?
For x?
Yeah, not for x, for p. P is greater than 1. That's when it converges, and it diverges for p less than or equal to 1. So basically, 1 is the boundary. Anything above 1, I get convergence. Anything else, I get divergence. So I think one of the ones we looked at last time was the integral of, I didn't save the ink, but we did do the integral from 1 to infinity of 1 over x. That does not converge. That's infinite. But 1 over x squared does converge for all those values. So now, and knowing that, what do we think this integral does? Should I get a number out of this? Or should I fail to get a number out of this? I should get convergence. I should get a real number. Why? P is greater than 1. So I get P equals 3/2, which is greater than 1. So we expect convergence. Let's make sure it happens. Is this an integral we can do? Or is this an antiderivative we can find? We can set up a U substitution. What's a good U? U equals x minus 2. Then what does du equal? Dx. And then I can set up this integral. I'll leave the bounds blank for a second. I get u to the 3/2 in the denominator. So really that, as far as our substitutions have gone, that one's pretty convenient. Are the bounds different? What's the lower bound? It's not 3 anymore. Should be 1. What's the upper bound? Still infinity, right? So again, infinity is not really a number, but what does it mean if I put infinity there? It means I'm going to let x get as large as I want. If I'm letting x get as large as I want, that means by the way I've defined u, it's also going to get arbitrarily large. So that bound is not going to change. But now we have this slightly different, but probably significantly simpler looking integral to do. How do we set this up? Take what? Take u to the top. Oh, okay, sure. So instead of that, we can integrate u to the negative 3/2 du. Good call. Now what? Okay, so let's do the, and what's the antiderivative of u to the negative 3/2? Negative 2 times u to the negative 1/2. So that's the antiderivative. What am I going to do with that?
Or I'm sorry, no, you could just.
We could. I'm gonna. We don't need to. So I can't really just plug in the bounds because of this infinity, right? So this is the kind of new thing we brought up last time. I'm going to bring in this new symbol t. And I'm going to take the limit as t approaches that. So the limit as t approaches infinity of this integral, or sorry, as this function as I evaluated at 1 and at t. So any question about why I'm doing this as opposed to just leaving an infinity as this upper bound here? Go ahead.
Question, why did the bound change from 3 to 1?
Good question. Why did that bound change from 3 to 1? Right. So basically, I know that from this substitution, u equals x minus 2. I can also use that to change my bounds. So the original lower bound was x equals 3. So u equals 3 minus 2, that equals 1. Basically, verbally, the biggest thing that substitution did for me was to reduce the variable by 2 everywhere we see it. So that's why the 3 became the 1. That's why the x minus 2 became u. Did I answer your question? Okay. All right, so now from where we are, how do I continue? Right, so now I can plug in those bounds because I'm not treating infinity like a number. So limit as t approaches infinity of negative 2t to the negative 1/2 minus negative 2 times 1 to the negative 1/2. Can I simplify any of this stuff? I'm going to rewrite some of these as square roots and as positive exponents because I think it's be easier to do. What is 1 to the negative 1/2? So this all just becomes plus 2, I believe. All right. So now that we have this, what happens to this as t gets really, really big? What goes to 0? The first term should go to 0, right? But the 2, nothing happens to it. So my final result should be 2. So we predicted convergence. We got it.
Convergence again is whenever it's greater than 1.
Whenever the exponent is greater than 1. Yeah, that basically in functions that look like this, convergence is totally tied to what that exponent is. But
If your interval was included to like two infinity,
Mhm.
and so you're gonna move it. What would happen if you were
sorry, where's the infinity there?
lower bound was started at 2, so 2,
Oh, so instead of the integral I gave you, we have this.
yeah. So the next would be
Why is that a problem? Right, so you're right to understand that that would be a problem. Because in that case, so let's talk about this first. We didn't really talk about it, but now that it's come up, let's do. Our original interval was from 3 to infinity, right? Is this function defined on this interval? So basically x is equal to 3 and larger. Should be defined for that, right? Is that true if I change that value to a 2? No, that doesn't work. So, but here's the thing. I'm integrating over things that might not be in my domain. We'll find out in just a few minutes that that's not always a problem. But in this case, would that be a problem? I think it would be, because at some point you'd be doing 2 over the square root of 0. So I believe in this case that would be an issue. We would get divergence if we tried to pull that lower bound back by 1 unit. So that's a really good question. We'll talk about some more specific examples with that. But yeah, this whole section is about improper integrals. There are other ways for integrals to be classified as improper other than the interval being infinitely long. So any questions about this one here? Okay, so now we still have an integral or an interval that is infinitely long, but now it's not bounded on either end. So how should I handle this? Any thoughts? Change my what?
Change your bounds to like a
Okay. As t goes to what?
So you'd have to set to t to going to infinity, and then you'd have to find a middle like 0.
Right. So this is the thing we got to pay attention to, is that limits are powerful, but they can only really investigate, at a single place. So the fact that I have this integral spanning like basically all across all the real numbers towards negative infinity, that means I need to split this integral up. So one side of this is going to be, now let's do it from left to right. Negative infinity to something. We'll talk about what that something is. But basically, I need to handle 2 different integrals.
Do you have to split it?
You do. Yeah. Basically, because if I'm going to set this up with a limit, so let's kind of write down what we were starting to talk about. Let's say I want to do limit as t approaches infinity. Well, then I'm looking at, by me calling that or writing that limit that way, I'm looking at this integral. I'm looking at what happens on the far right. So I can't use that same limit to look at the other side. I can probably set up a similar one, but I have to set up another one. Yeah, so really you have all kinds of freedom of what this number is, as long as it is consistent. Otherwise, you're not looking at, so for example, if I did negative infinity to 0 here and then 2 to infinity here, you're leaving off some area that I would like to know about.
So it just needs to stay the same.
It needs to be consistent. That's all. I think last semester when I did this example, we broke it off at 1. This doesn't matter though. Go ahead.
You ever have to worry about like the value that is defined between the interval?
Yeah, you didn't even look at that.
Okay.
Is that an issue here? So let's look at the function itself, x e to the negative x squared. Are there any x values that are going to cause that to be undefined? That should be okay. So you're right to suspect that you need to look for that, but in this case, that function is defined everywhere. How are we doing? So now we have to do a couple different integrals. I'm going to let one of them take t to negative infinity. I'm going to let another one take t to infinity. And basically, we're going to handle these integrals one at a time. The limit is t goes to negative infinity of this, t to 0 of x e to the negative x squared dx. And similarly, from 0 to t of x e to the negative x squared dx. Is this an antiderivative we can find? U substitution will work. So let's partition our screen here. What's a good u to do this integral? Negative x squared, which means du is negative 2x dx, which means the indefinite integral becomes what? X e to the u dx.
Negative, the x would cancel dx.
Okay, so first let's drop in let's solve for dx and we can substitute it. So this becomes du over negative 2x. So x e to the u times du over negative 2x. Cancel, cancel. And I get this, negative 1/2 times the integral of e to the u du. So that becomes negative 1/2 e to the u plus c. Okay, so now that we've done that, let's look at these individual integrals. The limit as t goes to negative infinity of, and I'm going to this time, so since the last one we just changed the bounds, this time I'm gonna do the other thing we talked about. I'm gonna just undo the substitution. So the limit is t approaches infinity of negative 1/2 e to the negative x squared from t to 0. I'm going to delete this and give myself more room. So negative 1/2 e to the 0 plus 1/2 e to the negative t squared. What happens to this thing as t gets really, really small? So what's going to happen to this negative 1/2 e to the 0? Yeah, times negative 1/2. So negative 1/2. But what happens to the other side? As t gets really, really small or goes towards negative infinity, what happens to 1/2 e to the negative t squared? I don't think it does go to 0. It gets very, very large. So let's talk about why. The limit as t approaches infinity.
Oh, yeah.
Actually, let me write this down because it might be easier to talk about. Is the thing I'm writing down right now equivalent to the thing that I wrote above it? So basically, instead of t going to negative infinity, I want t to go to positive infinity. So basically, I did double negation. So in making negative infinity into positive infinity, I'm no longer looking at a negative exponent. Go ahead.
Should that be negative 1/2?
No, I think this one is positive, right? It's
Minus a negative.
at some point it was like this, but I believe it should be net positive.
Is it?
Go ahead.
Is it, so when I was doing the homework, I was looking at the graph of what this would look like
Mm-hmm.
when it goes. You know, like, I don't know, but looking at the graph, so
Yeah.
you can see what rate it approaches as it goes to infinity.
Yeah, I believe this graph here. In fact, if it would convince you, we can look at it. this. This time I'll keep it. You can still, no, you can't see anything. Why would you be able to? Why did it go away? All right, we're gonna do this in the clumsiest way I can think of. So what was it? X times e to the negative x squared? Why is it not working for me? For some reason, I'm not able to get it. I'm not able to get it over there. But basically, so for some reason, I can't get it over there. But the left side of this graph does, it does get very large. So basically, that's why the convergence comes from that side. So we didn't do it, but if we were to integrate the positive side of this integral, so the right-hand side of the y-axis, we would have gotten convergence. But that doesn't matter if one end of this converges, or one end of this diverges, I'm sorry. So this right here, this limit is equal to infinity. So because of that, we have diverges. Go ahead.
The divergence in P is greater than
You're right. That doesn't apply to the things that look like this. The P series or P integral thing, that's really about integrals that are of this form, 1 over x to the P from a to infinity. Any more questions here? What time is it? Okay. How about this thing? Do we think this converges or diverges?
Converge.
Really? It is infinitely long. Not bounded on either side. It's a trick. What's the trick?
It's an arctan.
Okay, so if we recognize this function and its antiderivative, we can sort of jump straight to this integral from negative infinity to infinity of 1 over 1 plus x squared dx is equal to arctangent of x from negative infinity to infinity. So we know the antiderivative, but now what do we have to do with it? How do we get from, so we did the indefinite integral and handled that one okay. But now what do we have to do to look at the definite integral across all the real numbers?
You can set the bounds for tangent as, or arctan as negative pi over 2. Pi over 2.
Negative pi over 2 to pi over 2. Where's that coming from?
So if you see the graph, if you look at the graph of tangent or arctan,
Okay.
it's like, it's only going, no matter what happens, it will always be between pi over 2 and negative pi over 2.
So no matter how far left, so well, let's kind of backfill in the graph, but this limit or this integral I'm looking at is not bounded from above or below, right? So what do I have to do to actually try to find this value? Yeah, so I'm going to do, I'll just do that again. So the arctangent of x bounded from negative infinity to 0 plus the arctangent of x bounded from 0 to infinity. But each one of those requires a limit. As t goes to negative infinity here. So this becomes the arctangent of 0 minus the arctangent of t. What is the arctangent of 0? 0. Now the other side, that's going to be hard to talk about. What happens to the arctangent of t as t gets really, really small? So let's draw a picture to try to help with that. So P has said something we're going to rely on. When you take the arctangent of something, it's bounded between what two things? Negative goes from negative pi over 2 to pi over 2, right? It's limited above and below. So let's do this. Let's draw a triangle. And let's give arctangent t a name. Arctangent t, we'll call that theta. If arctangent of t is equal to theta, can I also say that tangent of theta is equal to t? Do those two things make sense? So let's start filling in this triangle. If that's theta and tangent of theta equals t, then I believe t is here, and I can put a 1 here. So does it still make sense what I'm doing here? Now, what are we trying to do with t? We're trying to make t really, really negative, right? We're trying to make t these numbers that have very large magnitudes but are getting more negative. So basically what we're doing here is kind of we're letting this triangle stay the same base length, but we're trying to sink its height, right? Trying to make that height longer and longer. If I do that, what's going to happen to that angle? It's going to change how? Is it going to get larger and larger? It's going to get larger and larger, right? But is it limited by something? Or does it just keep getting larger? What's that angle going to do? Go ahead.
It just approaches 90, right?
It approaches negative 90 in this case, but yeah. So in this case, that angle is going to approach, and I'm going to make us talk in terms of radians, so negative pi over 2. So what happens to this limit? This becomes 0 minus negative pi over 2, or pi over 2. So do we have convergence? I'm not convinced. We have convergence on 1/2 of this integral, right? But I think we still need to look at the other side. So what does this side do? The limit as t goes to infinity of arctangent of x from 0 to t. So this becomes arctangent of t minus arctangent of 0. So this arctangent of 0 is still 0. That's defined. what happens to the arctangent of t as theta gets really, really big? So now think about this triangle and invert it. That goes to 90 degrees again, pi over 2. So this becomes pi over 2. So do I have convergence? Absolutely. It converges to what? Pi. So into my two separate integrals, I got pi over 2, pi over 2. Final sum of pi.
That's adding both of those together.
Yes. So basically, if you think about it in terms of areas, I found the area on the left-hand side of the y-axis and the area on the right, so the total is their sum. How are we doing? All right. So let's get away from these infinitely long integrals, or infinitely long intervals. This has a finitely long interval. So the interval is 3 units long. So what's the problem? Why would this integral not converge? This integral is not even, this function is not even defined over that interval. Is that a problem? So this function, so this integral is this function 1 over radical x minus 2 is not defined at x equals 2. So because of that, should my integral converge? Or should it diverge? So we actually don't know. So in general, we don't know. So let's dig a little deeper. How do I evaluate this integral?
That your limit to something that's really, really close, approaching to the right.
So limit as x approaches 2 from the right.
So like splitting up into 2 again.
Do we have to split it up into 2? In this case, I'd say we don't. Why do we not have to do that in this case?
You'll have to see the left side of it.
I don't really care what's going on the left-hand side of 2. So our discontinuity happens at one of the bounds. So that is what saves us from having to look at this on either side of 2. I don't want to call it x because x is already doing a job. So limit is t goes to 2 from the right, from t to 5 of this 1 over radical x minus 2 dx. Is this an integral or is this an antiderivative we can find? What is it?
Substitution again.
Okay, what's a good u? X minus 2, which means du is dx. What happens to my bounds? This should become t minus 2, right? Hold that thought. For right now, we'll leave as t minus 2 to 3, right? Of u to the negative 1/2 du. Would it hurt anybody's feelings if I did this? The limit as t approaches 0 from the right of t to 3 u to the negative 1/2 du. Go ahead.
Can you just explain why you did that?
Yeah, I was gonna actually have somebody in here explain why I did that. I had a good reason. Any ideas what it was? Basically, I just wanted to make that lower bound, something a little easier to deal with. It is not by any means necessary. So, a couple reasons. If I can make the lower bound a single term instead of 2 terms, that's preferable, at least for me. Also, I really like looking at zeros instead of non-zero things. Typically, investigating at 0 is more simple. And I think it will be here. Okay, so what now? Are we ready for antiderivative? What is the antiderivative of u to the negative 1/2?
So then
Is it 1/2 u to the 1/2? Should be 2 u to the 1/2. Yeah, u to the 1/2 divided by 1/2, so multiplied by 2. So now I get this. So let's evaluate. No, not infinity. That's old. The limit as t goes to 0 from the right of this. So 2 times 3 to the 1/2 minus 2 times t to the 1/2. Does this limit exist? Certainly 2 times radical 3 is well defined. What happens to this other term as t goes to 0 from the right? It goes to 0. So this thing converges. So all the past integrals we looked at were these, if we think about it in terms of area, we were looking at these shapes that had their height could be measured. Their height was finite, but the length was not finite. It was infinitely long. So in this case, what do we have? If I draw a graph of this, 1, 2, what does this look like? It sort of looks like this. I have a horizontal asymptote at the y-axis or the x-axis and a vertical asymptote at x equals 2. And where am I actually looking from 2 to 5? So the area I'm finding is this shaded in right here. So this shape that I'm shading in, its base length is finite. It's only 3 units long. But how tall is it? It's infinitely tall. So that's why in some of these cases, these integrals will not be well defined, but in this one, it is. Basically, even though I have infinite height here, this, what's the right way to say this? This decrease is steep enough so that like the area that's in there is not significant enough to make it diverge. Questions here? Try again. Just similar to the last one. That's different for a couple of different reasons. So what do we need to do here?
change your bounds.
Change my bounds to what? Let me ask this: what's the problem with this integral? It's got a hole at 2. Is that a problem for us? So this is 1 over x minus 2 squared, undefined at x equals 2. So let's deal with that first. So I have a discontinuity. My domain does not include x equals 2. So what do I have to do with this integral to account for that? This time it has to be split up. 2 is on the interior. It's in between 0 and 3. So I split this integral up into 2 things. The integral from 0 to 2 of 1 over x minus 2 dx, x minus 2 squared dx, and the integral from 2 to 3. So let's handle these one at a time. Where do I go from here?
Since it has a hole at 2, you have to change it to.
Right, so let's do this one first. So we'll do the integral from 0 to 2. So I need to set this up as a limit. So the limit as t approaches what? 2 from the left this time. So I want my integral goes from 0 up to 2. 2 is a discontinuity, so I need to account for that. And for this first integral, I don't care about what's happening to the right of 2. So I can just do 2 from the left. So from 0 to t of x minus 2 to the negative 2 dx. Can we do that without a substitution? Yeah. The reason I'm asking is because we've done integration by substitution all the other ones, and why do I think we can get away with not using substitution in this case? Go ahead. Right. So let's briefly let me show you what the substitution would look like. I believe you would mostly agree that you should be equal to x minus 2, right? But then du and dx are the same thing, right? Because the du and dx are equal, I don't really have to, all the manipulation and juggling I have to do with the constants doesn't really show up. So because of that, I think I can just, what is the integral of something raised to negative 2? It's negative that thing raised to negative 1. Oh, no more integrals. So negative x minus 2 to the negative 1. So now what happens when we try to evaluate this? We get the limit as t goes to 2 from the left of negative 1 over t minus 2 plus 1 over negative 2. I'll call 0 minus 2 to show where everything came from. Are we okay with that? Let's talk about the part where t has nothing to do with it. I believe this right-hand term goes to negative 1/2, right? What happens to the left-hand term? I don't think it goes towards 0. I mean, sorry, what goes towards 0? The denominator goes towards 0. So what does that mean overall? It goes toward infinity, or is it negative infinity? I think it's going to go toward positive infinity. Because you're only taking values of t that are less than 2, right? Does that make sense? So if you're only taking values of t that are less than 2, then that 1 over t minus 2 takes on values that are extremely small, very negative. And then the negative on the outside makes it positive. So I think because of that, we get infinity. And the negative 1/2 doesn't factor, I mean, it gets overwhelmed by the infinite limit. So what did we learn here? Do we have to keep going? No. So if you want to convince you, or if you want to practice this and kind of investigate for yourself, this one diverges for a slightly different reason, but because we have divergence on half of this, we have divergence for the integral overall. So one thing I want to make sure I point out is that, you know, just like with infinite length, sometimes infinite length can converge, sometimes it can diverge. Having these infinitely tall areas, you need further investigation for these ones as well. Go ahead.
So basically it only converges if both the limits equal the same.
Yeah. So think about very early on in Calc 1, you probably talk about limits, right? And whether or not you remember doing it, you probably talk about like these things called limit laws. So basically, if you have like 3 limits that all exist, you can add all those functions together, and the limit at that point would just be the sum of all the limits, right? But those things only work if all the individual limits exist. That's the same kind of thing here. Remember that, we don't talk about it a lot, but an integral is a limit. It's what happens when you take a Riemann sum that's the area of a bunch of rectangles, and think about what happens when the rectangles get infinitely many and infinitely thin. So we are talking about a limit. So there's one that we did not complete because part of it diverged, but so this one diverged, right? So this right here diverged, but I will tell you that this one right here converges. So because both limits don't exist, I can't say anything about the sum of those limits. So all those ideas about divergence and convergence and integrals, they all follow suit from the way we talk about limits. Because really integrals are just specific kinds of limits. So yeah, they both have to so I think the best way for me to sum it up is this. If one diverges out of 1,000, then the whole thing diverges. But if you're taking a bunch of different integrals, or basically breaking up an integral into a lot of different intervals, they all have to converge. And if they do, the overall integral converges. But only one of them has to fail for the whole thing to fail. Go ahead.
Converge at the same value or just
Nope.
same value?
Oh, I think that's been a coincidence.
Okay.
They do not have to converge to the same value. They just have to have. They all have to have limits.
Okay.
Yep.
So if you get like a final answer of infinity or negative infinity, that counts as divergence?
Yeah. So, yeah. Let's revisit the definition of convergence. So let's say right here, if an integral from a to b of a function, if that converges, then what does that mean? Like what kind of result did I get from this? It's a real number. So yeah, which does not include infinity, negative infinity, limits that don't exist. So I have to have that convergence. I don't have to have all of them converging to the same thing. I think ours have worked out that way, but that's not necessary. We only have 2 minutes left. I don't think this example is, I don't think it's necessary to carry this one all the way through, but I do want to talk about what considerations we would have. So you might be tempted to look at this integral and just go, find the antiderivative, plug in 9, plug in 0, give me a number. Why is that a flawed approach here? It's undefined at 1. Is 1 inside my interval? Good. Is that the only thing I have to worry about?
It's undefined less than 1, 2.
It's undefined over. It's undefined at 1 and anything less than 1, right? So that's a problem. So one thing that I wanted to talk about, actually, this as much as we can say about this thing. It's one thing to have a single point where your interval is not defined, or your function is not defined in an interval. Let me ask this way: this thing is only defined from greater than 1 up to 9, right? As far as my interval cares about. How many discontinuities does this function have? An infinite number of them. That's a fatal error. You cannot make those converge. So we have seen improper integrals where if you have like a single point or like even like a finite number of discontinuities, the integral might still exist. But in this case, there are an infinite, basically every real number between 0 and 1. How many numbers is that? An infinite amount of it. So since we have that, we can't proceed. We already know this one diverges by virtue of me having an infinite amount of values on my interval where this function is not even defined. How are we doing? All right, so that's all for this section. We'll jump into a brand new chapter on Monday. I'll stick around for a few minutes. Otherwise, I'll see you Monday.